Welcome to this tutorial on how to implement a denoising diffusion model in PyTorch. On YouTube, I've already watched several great tutorials on these models. However, so far there's very few hands-on content. Because of that, I created another Colab notebook with an implementation of a simple diffusion model, and throughout this video I explain both the theory and the implementation and hope that you find it useful. With diffusion models, we are in the domain of generative deep learning. That means we want to learn a distribution over the data in order to generate new data. There are already lots of model architectures available to generate new data, for example, generative adversarial networks and variational autoencoders. I found this figure in NVIDIA's blog, which summarizes it quite nicely. VAEs and also normalizing flows have shown to produce diverse samples quickly, but usually the quality is not great compared to GANs. As a recap, a VAE compresses an input into a latent distribution and then samples from this distribution to recover the inputs. After training, we can sample from the latent space to generate new data points. Usually VAEs are quite easy to train, but as mentioned, the outputs can be blurry. GANs, on the other hand, produce high quality outputs, but are most of the time difficult to train. This stems from the adversarial setup, which can cause problems such as vanishing gradients or mode collapse. I have to say that I experienced lots of these issues myself throughout the years. Of course, there are already lots of improvements nowadays, but still it's not that easy to fit such a model. As you probably know, the diffusion model is a rather new generative deep learning model that has shown to produce high quality samples which are also quite diverse. Diffusion models are part of a lot of modern deep learning architectures and recently showed great success in text-guided image generation, such as in DALL-E 2 or Imagen. I'm pretty sure you have seen this in the media. Diffusion models work by destroying the input until noise is left over and then recovering the input from noise using a neural network. More details will follow later in this video. Of course, diffusion models also have their downsides, for example the sampling speed. Because of the sequential reverse process, they are much slower compared to GANs or VAEs. But as these models are still in their infancy, there might be lots of improvements in the future. Using that as motivation, let's try to build a simple diffusion model by ourselves. More specifically, we will fit a diffusion model on an image dataset. The architecture and model design are mainly based on the following two papers. The paper on the left from researchers from Berkeley University was one of the first publications that uses diffusion models for image generation. The researchers demonstrate what this model is capable of and also introduce some nice mathematical properties. The paper on the right from OpenAI can be seen as a follow-up with several improvements that make the image quality even better. For example, they use additional normalization layers, residual connections and more. In my simple example, I don't plan to build the latest state-of-the-art architecture, but instead just want to build a solid base model. Finally, I want to point out that this video is focused on the implementation and not all of the theoretical details. Of course, I will explain everything that is required to follow along, but in case you really want to get a deeper understanding, you might want to have a look at one of the great resources collected on this GitHub page. With that being said, let's continue with answering some immediate questions about implementing diffusion models in a fast-forward mode. First question, what are actually diffusion models? Diffusion models work by destroying some input, for example an image, by gradually adding noise, and then recovering the input from the noise in a backward process, also called denoising. This is also called a Markov chain because it's a sequence of stochastic events where each time step depends on the previous time step. A special property of diffusion models is that the latent states have the same dimensionality as the input. The task of the model can be described as predicting the noise that was added in each of the images. That's why the backward process is called parametrized. We use a neural network for it. In order to generate new data, one can simply perform the backward process from random noise and new data points are constructed. A typical number of steps that is chosen in this sequential process is 1000. However, of course, the larger this number is, the slower the sampling will be. Next question, how do you start implementing such a model? We will need mainly three things for that: a scheduler that sequentially adds noise, a model that predicts the noise in an image, which will be a UNet in our case, and finally a way to encode the current time step. We will dig deeper into each of these components, but first let's have a look at our dataset. So this is the Colab notebook, and the dataset we use is called Stanford Cars, which is included in PyTorch, and it consists in total of around 16,000 images, 8,000 train and 8,000 test images. Of course, as we build a generative model, we can use all of them. So we have 16,000 images, and here are some samples of them. Later I will crop them to the same size and reduce the size a bit to make the learning faster. As you can see, the cars in these images are in many different poses with a variety of backgrounds, so we should expect a lot of diversity in our generated images, which we will also see later. Of course, there's no need to reinvent the wheel. There are already some existing implementations of diffusion models, and this notebook is highly inspired by these implementations, which means I got a lot of the code from these two resources. Implementing the diffusion model consists of several steps, mainly the forward process, the backward process, the loss function, and then we can already define sampling and training. And before we start looking at the forward process, let's talk about it in more detail. Even though I try to keep it practical, we have to talk about some of the math of diffusion models. The forward process is fairly easy. All we need to do is to add noise to the images. This Markov process is usually denoted with Q, and the noise that is added to an image depends only on the previous image. X0 is always the initial inputs, and all other X's are more and more noisy versions of it. The way how noise is sampled is described by this formula. It's a conditional Gaussian distribution with a mean that depends on the previous image and a specific variance. Let's inspect this term more closely. The sequence of betas is a so-called variance schedule that describes how much noise we want to add in each of the time steps. xt-1 is the previous less noisy image, which means the mean of our distribution is exactly the previous image multiplied with this term that depends on the variance schedule beta. The variance of this normal distribution is fixed to beta multiplied with the identity. I thought it makes sense to gain some more intuition about beta. As you probably know, each of the pixels in an image has three channels: red, green and blue. These values are usually between 0 and 255, or when normalized between, for example, -1 and 1. Let's take this giant red pixel with a color code of 1, -1, -1. So we have a lot of red, but no green and no blue. According to the previous formula, the distribution of our next image is now described by this mean and variance. That means the values of our red pixel multiplied with the square root of 1 minus beta is exactly the mean of our distribution for that single pixel. Depending on the noise level beta, this could for example be 0.99 for the first image. The variance is fixed to beta. If we choose a large beta, it means that the pixel distribution is not only wider but also more shifted, which results in a more corrupted image. When sampling from this distribution, we consequently end up with more noise. Eventually, beta controls how fast we converge towards a mean of 0, which corresponds to a standard Gaussian distribution. I recommend to try out different values to see how the means converge towards 0. The important part is to add the right amount of noise, such that we arrive at an isotropic Gaussian distribution with a mean of 0 and a fixed variance in all directions. Otherwise, the sampling later will not work. That means we don't want to add too few noise, but also not too much in order to have a too noisy image too early. There are different scheduling strategies for that. In our case, we will simply add the noise linearly, but in the literature there are also choices like quadratic, cosine, sigmoidal, and more. I said that the noise is added sequentially in this formula, but actually the researchers proposed an even better solution. Because the sum of Gaussians is still a Gaussian distribution, we can also directly calculate the noisy version of an image for a specific time step t. And that's without sequentially iterating over its predecessors. Based on the initial image x0, we can sample the noisy version of it for any arbitrary time step t. For this, we need to pre-calculate the closed form of the mean and variance based on the cumulative variance schedules. Let's see an example of this to better understand it. Let's say we choose 200 steps in our diffusion process. The variance schedule beta tells us how much noise we want to add in each of the steps. We linearly increase it until a maximum value of 0.02. If we wouldn't increase it at all, it would take forever to end up with pure noise. The authors now define the term alpha, which is simply 1 minus beta. I like to think of it as a number that tells us how much information of the original image we keep when transitioning from one image to the next. By calculating the cumulative product of these alpha terms, we get a new term denoted as alpha over line. With this, we can specify a new distribution that allows us to sample for a specific time step. Now that's the high-level explanation. For more details, I recommend to have a look at the extraordinary explanation video by Outlier that captures all the mathematical derivations for which I didn't have time here. A consequence for our training will be that we simply sample a time step t and pass the noisified version of it to the model. That makes the training much easier and smoother compared to sequentially iterating over the same image. That was mostly it regarding the forward process. Let's jump into the code and see how we can implement it. Alright, let's have a look at the noise scheduler. This is mainly inspired from the GitHub implementation. First, we have a function that defines a linear beta schedule. We use torch linspace for that, which interpolates between two values for as many time steps as we define. So these are the betas. And then this is just a helper function that extracts a specific index from a list and also considers the batch size. So we can use it later and during training. And the main function is forward diffusion sample, which will use some pre-calculated values from here. And those are exactly the values I just mentioned. So we calculate the alphas and then the alpha with the overline and some additional terms so that we can calculate the noisy version of an image. So this function takes as input x0, the initial image, and the time step t, and it returns the noisy version at time step t of that specific image. And so what's happening in this forward diffusion sample function is that we sample some noise and then get the time step specific values that are pre-calculated. So we get a specific index from all of these pre-calculated lists for alpha overline, square root, and all of that. And then we simply calculate the new sample based on the original inputs plus the noise, and this gives us the noisified version of an image at a specific time step. So next we can try that out on our data set, but in order to do that, we first have to put our data set into a PyTorch data loader. And also our images at the moment are pillow images, which means we first have to convert them into tensors. And as mentioned before, I resized the images to a shape of 64 by 64, which is relatively small, but makes the training much faster. And then I do some data augmentation things like horizontal flips. And then I call toTensor, and this scales the data between 0 and 1. And now I mentioned that we need to have the data in a range of -1 to 1 in order to work with these betas. And because of that, this last transformation converts our data into our desired range. And that is because if we multiply that by 2, we have a scale of 0 to 2. And then if we subtract 1, we end up in the desired range of -1 to 1. And then, as mentioned before, I load both the train and test sets, and then I merge them into a so-called concat dataset, which holds all of the images. And then I have a second function that does exactly the reverse direction. It converts a tensor image into a pillow image and applies all of the reverse transformations that we did here. And after that, it simply shows or prints the image. And if we have a batch of images, we just take the first image to display it in our notebook. And with that, we load the data set, so train and test split, and then put everything into a data loader. And here we can simply iterate over one batch and see how we convert an image into more and more noise so that we end up with pure noise. So now, after finishing the forward process, let's have a look at the neural network model in the backward process. The authors propose to use a UNet. This is a special neural network that has a structure that is similar to the one used in an autoencoder. UNets are a popular model for image segmentation, and their output has the same shape as the input. The input passes a series of convolutional and downsampling layers until a bottleneck is reached, and then the tensors are upsampled again and pass more convolutional layers. The input tensors get smaller but also deeper as more channels are added. Besides that, there are a lot of other components that are typically part of these UNets, such as residual connections between the layers, batch or group normalization, and also attention modules. As mentioned before, I aim to build a very simple and easy to understand model, and that's why I only use the main components of this architecture, such as down and upsampling, as well as some residual connections. One constraint of diffusion models is that the input needs to have the same dimension as the output. Because of that, the UNet is a great fit for image data. Our model will take a noisy image with 3 color channels as inputs and predict the noise in the image. Because the variance is set fixed, we will only output one value per pixel. That means the model learns the mean of the Gaussian distribution of the images. This is also called denoising score matching. Note that there were also experiments with predicting the image mean instead of the noise mean, and both approaches seem to work. One important thing is that we need to tell the model in which time step we are, because the model always uses the same shared weights for each input, no matter if it's 45 or 8. We will talk about this component in a second. The reverse process can also be formulated mathematically like this. We start in xt with Gaussian noise with a mean of 0 and unit variance. Then in a sequence, the transition from one latent to the next is predicted. This makes the model learn the probability density of an earlier time step given the current time step. As mentioned before, during training we just randomly sample time steps and don't go through the whole sequence. At sampling time, however, we need to iterate from pure noise in xt to x0, which is the final image. The density P is defined by the predicted Gaussian noise distribution in the image. In order to get the actual image of time step xt-1, we have to subtract this predicted noise from the image xt during sampling. This is just a rough formula to give you an intuition. The exact one in the paper also considers the noise levels beta. Again, if you look for a deeper explanation of this, check out Outlier's math video. Okay, now we have captured the 2 most important parts of diffusion models. Finally, let's talk about how we can consider the time step in our model. The neural network has shared parameters across time, which means it can't distinguish between the different time steps. That, however, means it needs to filter out the noise from images with very different noise intensities. To circumvent this, the authors used positional embeddings which were presented in the transformer model. They are a clever way to encode discrete positional information like sequence steps. Positional embeddings can be visualized like that and have the task to assign a different vector to each index. For example, if you have the values 1, 5, and 10, the corresponding embeddings could look like this. The embeddings are typically calculated using sine and cosine functions for a specific embedding size defined by d in this case. For more details, I recommend to have a look at the Machine Learning Mastery blog post in the video description. The positional embeddings are then simply added as additional input besides the noisy image and used in several places in the model. Now that we are familiar with all the building blocks, let's see how we can implement this in practice. So this is the backward process and the UNet implementation. Let me quickly show you the code so that you see that it's not too much, because I really tried to make this model as simple as possible. That's why it's also called Simple UNet. So let's go over this step by step. The incoming image, so the noisy image, has 3 channels for red, green, and blue. And we extend these channels by applying learnable filters in these convolutional layers so that we have more and more channels, so the depth of our tensors increases. And this happens until we have 1024 channels. And then in the up channels, we again reduce the size. And besides that, we also increase and decrease the size of the images, and we will see that in a second. All of that happens in these blocks. And in the forward function, we simply iterate over each of these blocks, pass it the current image, and get an updated version of the current image with more channels and a smaller or larger size, and then we pass it again. And in addition to that, we also include the time step in form of a positional vector. And as mentioned before, we use positional embeddings for that. And here is how we can calculate them using sine and cosine functions. And this returns a vector that describes the position of an index in a list. We also have an initial projection layer that converts our image to the first dimension, so to these 64 channels, and then a readout layer that uses the last dimension, again 64, and converts it again to 3, which are the number of channels our image has. And now the only question left is what is happening in each of these blocks. Each of these blocks applies 2 convolutional layers to the input image and also considers some additional things. For example, we apply ReLU activation functions, we use batch normalization, and then we also consider the time embedding. And for that, we first transform the time embedding to match the current number of channels and dimension we require in this specific step. And then we simply add the time embedding to the current embedded image. And so we have basically, we add the channel of the time embedding, and then we apply the second convolution. And this gives us a representation of the image that contains both the time step but also the image information. And finally, we down or upsampling. And depending on if we are in an upsampling or downsampling block, we use either this transpose to 2D function or layer, or if we downsample, we use this with a specific padding so that we end up with a downsampled version of our image. So I won't go deeper here, but I can recommend to have a look at this post, from which I also got some inspiration for doing these implementations. The last part I want to mention here is the residual connections, and this is simply done by storing all of the transformed images in the downsampling steps, and then simply recovering or reusing them as additional inputs by adding this residual connection. So that means The input in our up layers will have both the upsampled image and also the residual connection from the downsampling steps. And then we have a final output that gives us the noise, the predicted noise distribution in the image. And these models can get big quite easily. So this one has 60 million parameters and is not even big. As said, you can extend this architecture by a lot of things: group normalization, attention modules. I recommend to read the second paper I mentioned at the beginning of this video, which implements a lot of these additional changes. The last and final part is the loss function. Diffusion models are optimized with the variational lower bound, similarly as it is done in variational autoencoders. However, as the authors bridge the connection to denoising score matching, they propose an alternative formulation that is equivalent to using variational inference. To make it short, the final loss function is defined by this and simply means we calculate the L2 distance of the predicted noise and the actual noise in the image. This loss function is pretty easy, but there are quite some derivations and considerations to arrive at this simple term, which I couldn't include in this hands-on video. It is, however, highly recommended to look into some of the literature to get a better understanding. So based on that, the loss function is straightforward to define, which simply means we have the L1 or L2 loss. So I tried out different approaches between the noise and the predicted noise. And this function getLoss simply takes an image, a specific time step, and our model, and returns the loss of the predicted noise and the sampled noise. The final part before training is the sampling, because we need to be able to generate new images. And I wanted to test that during the training. So I first define these functions here. And the first part is that we should put a torch no-grad decorator before each of these functions. And because of that, we don't track all of the previous images for gradient calculations. And if you don't do that, you will quite quickly run out of memory. Sampling is straightforward. All we need to do is we pass some image to the model and also a time step, and we get the predicted noise in this image. And then we simply subtract this noise from the real image. And if we do this in a sequence, so in a for loop, which happens here, we can iteratively get less and less noisy images. Again, we will need our pre-calculated noise levels here according to this algorithm in the paper. And by doing this, we can get less and less noisy images. And if we're in time step T, we will return the image noiselessly. In all other steps, we will add the noise that is added according to our forward process. And down here, I simply do exactly that. So in a reverse sequence from T, which was 300 in this example, until 0, I iterate over the images and pass the images to this sample time step function, which returns a less noisier version. And every X, or number of step size images, I plot the image which we will see in a second in the training. So the training part simply means we iterate over the data points in our data loader, and then we call this getLoss function, and then we simply optimize the model. And doing this looks more or less like that. At first, I was a bit disappointed by the results and thought my UNet needs some rework. On Colab, I trained the model a bit longer for around 100 epochs and started to see something like this. I mean, I wouldn't drive with these cars, but it certainly goes in the right direction. Unfortunately, I hit the usage limits on Colab so that I couldn't try out more epochs. Because of that, I decided to fit the model a bit longer on my personal GPU, and after around 500 epochs, I got these results. Now, these are clearly cars. Of course, the resolution is still very small, but I was pretty happy that I made it this far. I think if you even train longer and do more refinements of the model architecture, you can clearly achieve high quality images here. Of course, diffusion models are not limited to image data. There's already a lot of work done in other domains such as molecule graphs, audio, and more. I also wanted to point out that there are already very interesting variants of diffusion models, such as diffusion GANs. Overall, I think that these models are a very promising family of generative models, and I really look forward to where this is going. That's the end of this introduction to diffusion models. Congratulations if you made it until the end. I hope you found it useful and would be happy to see you again in a future video. With that, have a nice day and happy coding!